We've got a lot to cover, so let's get started. My name is Jared Cannon, and with me and my colleagues, Chris Kaczynski, Dat Lee, and Roger Cummings, we're going to discuss special relativity. I'm first going to start by giving you a general overview of general relativity. General relativity has two main assumptions. They are the laws of nature are the same in different frames of reference, and that gravitational mass is the equivalent of inertial mass. With that said, general relativity is the overarching theme of Einstein's 1914 paper to try to relate the space and time of the universe to a layer of, like a thought experiment, to relate the fabric of space and time to gravity, and to try to be able to explain and quantify gravity on a universal scale. So with that, we're going to go into special relativity, which has another set of assumptions related, that is that the laws of nature are the same, are constant in different inertial frames of reference, and that the speed of light is constant in a vacuum. The speed of light is a big part of the theory of special relativity because it relates to the way that we have length contraction, mass increase, and time dilation as we get closer and closer to the speed of light. That said, the basis of the theory is that nothing can ever travel faster than the speed of light, because if you could travel faster than the speed of light, then you can make time go backwards, which is bad for everyone. That said, we're gonna have Chris Kaczynski go into the effects of time dilation.
Hey everyone, I'm Chris Kaczynski. Topic that I'm going to talk about is time dilation. Time dilation is the difference in elapsed time between two events relative to an observer. There are two different ways that we measure time dilation. We measure it by velocity or gravity. Objects that are higher in velocity, they have a slower time, and objects near higher gravitation, they actually have a slower time as well. There are two things that I wanted to talk about for time dilation. It is the twin paradox and the Hayfele-Keating experiment. The first one is the twin paradox. The twin paradox is the idea if you have two twins and right at birth one of the twins was sent in a space shuttle and another one stayed on Earth, you could actually find out how much younger the twin in the space shuttle will be by using this equation. This is the inverse of the Lorentz factor. And basically the value that you get from this equation is the proportion of the age of the kid in the shuttle compared to the kid at Earth. So for example, they found if the kid in the space shuttle was going at 80% the speed of light, then he would actually be 40% younger than the kid that stayed on Earth. So for example, if he was going for 10 years in Earth time, then he would actually be only 6 years older when he got back to Earth, 10 Earth years later. The other thing I wanted to talk about was the Hayfele-Keating experiment. In this experiment, Joseph Hayfele, he's a physician, and Richard Keating is an astronomer. They took 4 atomic clocks and put them in aircrafts, commercial aircrafts. They flew each aircraft around the world twice, once from once from east to west, and the other experiment from west to east. And actually when they came back, the atomic clocks were 0.065 seconds slower than the clocks that they left in the U.S. Naval Center.
Thank you, Chris Kaczynski, for that amazing description of time dilation. Next, we've got Dat Lee coming up to describe length contraction.
Well, ladies and gentlemen, good evening, good morning, wherever you may be. We are going to discuss length contraction. So, gentlemen, don't be afraid, this is not apply to you specifically. So, with length contraction, we are going to begin with an experiment. As is in physics, everything that can be proved needs to be proved empirically. So, experiment number 1. Did you catch that? I'm going to do it one more time. So, if you wonder what I'm doing, what the length contraction as postulated by Albert Einstein says that any object moving with a non-zero velocity will experience a length contraction. So does that mean that as I moved, that I got thinner? Because that would be the best weight loss program in the world. Unfortunately, at non-relativistic speeds, it is negligible. So in everyday life, what you experience as things moving through, you won't see a length contraction, but it is there. However, it will be imperceptible to the eye. So moving on, length contraction, it kind of breaks several different ideas that we think should be constant. Length should be length, it shouldn't change regardless of where you are. Unfortunately, when we're dealing with Einstein's special relativity, things that we think are constant, they change quite a bit. With Einstein's idea of length contractions, he is saying that when we move at relativistic speeds, that length will contract. Now, when we hold that, we are taking two different reference frames, where one would be stationary and another reference frame with an object moving at near the speed of light. What the person at stationary will see is almost a thin line, because when you move at that kind of speed, your length will contract, however your height will remain the same. Mr. Hendrik Lorentz actually created a formula to kind of tell us what the length that you would perceive might be. The formula is going to be the length that a person at stationary will see is the length of the object with the square root of 1 minus their velocity squared over the speed of light squared. So the closer that they get to the speed of light, the thinner the object will be that is perceived. So I did have an example for you here. We are testing the speed of a spaceship versus a person on the ground. So at rest, the observed length would be 200. They're not moving, and neither is the person viewing them. And their height would be 40 feet. Now, when you're going 10% the speed of light, what you're going to see is that the observed length will be 199. So you lose 1 feet at 10% the speed of light. However, height will remain the same. When we go 86.5% speed of light, that's going to decrease by half. So the person on the ground will see half the length of the spaceship than it was originally at rest. Again, observed height will remain the same. When you're going faster than that, 99% the speed of light, you're only going to see 28 feet of the spacecraft. And then when you're going 99.99%, the spaceship that was originally 200 feet will be reduced down to 3 feet. They say when you go to 100% the speed of light, you're not going to see anything. The length decreases so much where it's negligible in the observed length. However, it is still there. So this isn't errors due to observation or errors due to mathematics. This is just what happens when you have two different reference frames and when one is moving at relativistic speeds. So it does change the game a bit.
Hello everyone, I am Roderick Cummings and I'm going to do my best to try to explain mass increase during special relativity to you. So normally we think of mass as an intrinsic property. We usually say that mass depends on the number of particles within an object, and this is true. You cannot change the mass of an object without removing particles from said object. Therefore, the velocity of an object cannot influence the intrinsic mass that something holds, the number of particles that are contained in that object. What we will consider is the relativistic mass of an object, and that is the mass that you have when you start to acquire speeds of that are comparable to the speed of light. Einstein proposed a theory that energy and mass are almost equivalent in the sense that energy is equal to mass times the speed of light squared, where the speed of light is constant, and that sort of makes mass directly proportional to energy. Now, at rest, this equation still applies. As the speed of an object increases, it takes more and more force and energy to further accelerate that object, because in a sense, the universe is resisting the motion of that object. The reason this doesn't happen with light is because light is massless, and therefore, and since it's also, you have the duality of light as both a wave and a particle, the speed of light is almost instantaneous, and so it doesn't have this resistance to motion that regular objects will. Now, as for a regular object, when you increase the speed further and further and closer to the speed of light, that motion is resisted more and more, and therefore it takes more and more energy. And as the energy of the object increases, the mass, the relativistic mass, must therefore also increase, since energy and mass are directly proportional and the speed of light is constant. Now, the intrinsic mass of the object isn't changing, but the relative mass of an observer, the relative mass of the object from an observer seems to change as you approach speeds closer and closer to that of the speed of light. So what's happening is, because you're approaching this speed, this ultimate speed, it takes more and more energy to propel you to that point, and your mass starts to get infinitely larger, and therefore it would require an infinitely larger force to get you to the speed of light. This is why Einstein's theory, or this is what confirms that Einstein's theory says that the speed of light is the max speed that an object that has mass can go, because light is massless and achieves this speed. Therefore, something with mass is limited by that quantity of speed. And due to the E=mc² relation, speed of light being a constant, the relativistic mass of the object must also increase as its energy increases.
Wow. Wow. Just wow. Roger, that was an amazing segment on mass increase. I had no idea that we could weigh that much, potentially. I'm here again. Lucky you. We're just going to sum up the topics that we discussed, of course. We're going to start with time dilation. I just want to reiterate that, because I fully am lost. Like, I don't understand how a particle. So Chris, what you're telling me is that a particle that is approaching the speed of light will actually decay slower than the same exact particle not traveling at the speed of light.
Yes.
Fascinating stuff. Fascinating stuff. And now, as you see with the picture behind me, we kind of have a diagram illustrating the idea of length contraction. I'm still trying to wrap my head around it. I mean, pictures are worth 1,000 words. So apparently, this rocket is traveling at a regular speed, let's say 0.5% of the light speed on the top picture. And on the bottom picture, we actually have it traveling roughly about 60% the speed of light. And so it looks like the contraction is ratio-wise around 50% contraction. Dad, is that possible? Is that how it works?
Sure, that's exactly how it works. You're absolutely right.
Unbelievable to believe that we live in this time, in this space and time. I mean, literally, we live in this space and time. We're a prisoner of our own time. I hope you enjoyed this segment on special relativity. Next week on Data, we're going to be talking about the theory of everything.
Keep that in me. What do we want? Oh, yeah, do we want that or no?
Equation is it's a modern marvel. We're going to be talking about the theory of electron. The theory of